All right, welcome. Today I'll be talking about our experience running on the Capitan system with the Empire Plasma Physics Code. There was a large team, a bunch of people are here at the conference, so I think Christian and Jonathan and James are all here as well. Okay. I do want to thank some people. Kevin actually is here too. From AMD and HPE who helped make this successful, and of course the COE from Livermore and Sandia. Okay, so we're going to be talking about invisible threats, and in this case I'm going to be talking about radiation, in particular X-rays. So when we have things like, say, a nuclear weapon blast, it releases a lot of energy. Most of it's in the form of X-rays. And what we want to do is make sure that our electronics components continue to function under these conditions. But if we have electromagnetic energy, electromagnetic pulses, it could disrupt the operation of the system, of the electronics. It could do physical damage to the electronics as well. So here's just an example. This is an experiment that we run at Sandia's Z machine and Livermore's National Ignition Facility. This is a cavity. It's an end-irradiated cavity. We have X-rays coming in from the top, strikes the surface, and what you see coming off there are electrons. That forms a plasma in the cavity and forms an electromagnetic field. This electromagnetic field can actually drive currents throughout electronics within the cavity. And so in the bottom left there's a gold wire there. We're measuring the current generated by this plasma. So this is the type of analysis we're doing for different components. At the end of the day, we want to measure the currents generated and make sure that we build our electronics to survive those currents. So Empire, it's a plasma physics code. This is next generation. It was built on top of Kokkos during the ECP days. This is just a simulation of the Z machine at Sandia, electric field on the left, electron densities on the right. This is just firing a shot to test some components. Empire self-consistently couples plasma dynamics to an electromagnetic field. So we solve the electromagnetic field implicitly. It's a linear solve, and we couple that to a PIC code. So we also have extra physics, collisions, we have ionization, excitation, and elastic scattering, and then we can couple the response to circuit codes. Once we compute the currents, we pass those off to circuit codes to see how a circuit might respond. So what we do is we solve the coupled Boltzmann equation with Maxwell's equations at a high level. The way we do this, for Maxwell's equations, we do unstructured finite elements, and we're doing just a fully coupled field solve of Maxwell's equations. We couple that to particle and cell for the Boltzmann equation, so we're evolving a collection of macroparticles self-consistently with the electric field. And then for collisions between particles, we do direct simulation Monte Carlo. So we track neutrals, electrons, ions, excited states, photons. And then we have this fully coupled solve. So within a time step, what does this look like to us? We're going to take, in our simulations, we can take hundreds of thousands of time steps. In each one, we're going to move the particles. We know their velocity, we know a delta t, we know how they're going to move. So they have to move a certain distance. When charged particles move, they're going to generate current. So we're going to have to weight the current within each cell, and this really is just evaluating how much current is generated. That drives an electromagnetic field, so it acts like a source term to Maxwell's equations. So then we're going to have to solve the electromagnetic field on the mesh. Once we have the new updated electromagnetic field, we're going to calculate the values at each particle position, and we can use those values then to accelerate the particles. Then we're going to go on to collisions, and this is local to each finite element cell. We're going to do pairwise collisions between all the particles in the cell. Then we're going to end up doing particle controls, and this is where we don't want the number of particles exploding and using up all the memory, so we run out of memory. So we're going to do what's called a merge. We're going to limit the particles per cell by combining particles. We merge particles together. And then we have to handle particle sources, so emission coming off boundary conditions or within the volume being created. So there's really three large tent poles in this, and the first is the move particles in the upper left there. That is, in terms of performance, it's basically three major operations. Move particles. Now the second major operation is the electromagnetic solve. So here we're forming a block system. We're solving for the magnetic field and the electric field. This is a compatible discretization, so they use different finite element bases. Magnetic field is an H-div, electric field is an H-curl. We form this block system, and then we're going to solve that with Trilinos. The third tent pole is going to be collisions. And again, it's just pairwise two-body collisions. So if you think about this from a GPU standpoint, this is a lot of kernel launches. We're assembling a PD, we're solving a PD, doing a linear solve, but on top of that, we're coupling it to all these steps with the particles as well. And each of these is going to launch a series of kernels. So this code was built on Trilinos, and we chose a very component-heavy integration here. So we started with Kokkos and Kokkos kernels for performance portability. For the electromagnetics, we're using a full linear solver stack, so Mulu, IFPAC, Mesos, you can read them all there, Balos. And on top of that, we do the finite element assembly using discretization packages. So this is very heavy. We're using about 38 packages out of Trilinos. So just to dig a little bit deeper to show you how we're using Trilinos, this is the block system. We can actually form a Schur complement and just solve one linear solve of this Schur complement system right here, and then do a back solve for the magnetic field. Okay. Pointer. Yep. So in terms of this, I've broken it down into packages. For meshing, we use Stick, Percept, Seekis, and Panzer. That gives us all the capabilities we need, including periodic boundary condition support, things of that nature. Our data structures, obviously, for on-node local, we use Kokkos and Kokkos kernels. When we do parallel distributed, we go to T-Petra. We wrap the Kokkos data structures in T-Petra. In terms of finite element assembly, we use the DOF manager out of Panzer. We have the Thera abstractions to form this block system. We used to solve it with TICO, but now we found a simpler approach. We didn't actually need the block system. And then we use Intrepid 2 for the bases. So our linear solve, it's conjugate gradients. We use Mulu's Ref Maxwell AMG preconditioner, Chebyshev smoother, and because the matrix is actually static and we just update the right-hand sides each time step, so we're forming the preconditioner once and then just solving over and over and over again. So these are the packages that we use here. What we find is that most of our linear solves are latency bound for real problems. So let's look at some results here. So the hardware comparisons we're going to do, there's 3 machines. So the base machine, it's called, we ran on Amber, it's CTS2, so that's dual socket Sapphire Rapids. That's our baseline capacity machines. Then we have an ATS2, this is Sierra. ATS2 was 4 V100 and NVIDIA V100s chips per node. And now we've got El Capitan ATS4, that is 4 MI300As per node. So if you're curious, these are statistics on the right, just showing what El Capitan is. Right now it's listed #1 on the top 500. It's got 11,000 nodes, so 44,000 of these MI300A processors. We're typically memory bound, so really what you want to look at is the relative bandwidth block. And you can really just ignore the peak floating point operations. So the first problem is going to be a comparison. This is called our simple cavity problem, and we're just going to compare ATS2. We had results from a milestone in 2020, compared now to ATS4 on El Capitan. So this is a simple test problem. We're going to preload the particles. We start it up, and there's uniform particle loading already in there. We're going to do a short burst of 100 time steps just to get performance. So this is kind of our performance monitoring tool. It's not a realistic system, but it gives you an idea of what the algorithms are capable of. And I have to say, it's not really a fair comparison in the sense that it's not apples to apples. There's been 5 years of development on Empire. ATS2 no longer exists. It was decommissioned. ATS4 is in its place, but we at least can get a baseline comparison. So over 5 years, there's been a lot of work, both in Trilinos on the solvers and in Empire. We have added much more complex physics. The kernel sizes have grown, more boundary conditions, and that really caused a lot of extra temporary views for these new physics. So the amount of registers you might need for a device kernel has increased because we have more Kokkos views in each device kernel launch now. So, yeah.
Those columns, the rightmost columns, are they switched adders?
This is the low number of nodes. So it's the number of nodes. So think of it, if you do a strong scaling study from 1 to 8, that's the number of elements at 1 node, that's the number of elements at 8 nodes. So yeah. So we've got 4 meshes. We're going to do uniform refinement, roughly 600,000 finite element cells at the low node count, at the high node count, yeah. So these are the results. The main time loop is on the right-hand side, so this is time per time step. Each color is a mesh refinement level. And the transparent, the lighter color, that's the ATS2 result we got back in 2020. And the solid color is now what we're getting on ATS4. So if you look at relative bandwidth purely here, we should have seen about a factor of 4. On GPUs, we do not get that, okay? There's a lot of reasons for this, and I can talk about some of them. But we do see a pretty good performance increase. And if you look at the large node counts, say the red mesh, the R4, you can see that our linear solver performance actually improved. It's probably hard to see the ideal strong scaling line. It's a lightly gray dash line there. But you can see over here, if we look at the individual timers for the tent poles, the linear solve and the particle push over here, the triangles is the linear solve, and you can see where it was flat and now it's strong scaling very well. So this is actually very impressive. We're pretty happy with this. So at least it's showing that the algorithms do strong scale to a degree. They're not perfect, but they look pretty good. The next problem, this is a real experimental problem. It's a radiation-driven cavity. We're going to solve on basically R1 through R3. We actually did not get R4 to run on the node counts that we launched them on. We think we were running out of memory, so we're going to have to go to larger node counts. We didn't get that finished. But we're going to start here, and this is a little different. It starts empty. There's no particles, and then the particles are going to enter the domain through boundaries. They're going to flood in and then flood out. So this will be a pulse event. This is a lot less work. If you'll notice, it's about 1/4 of the work of our scaling runs. So the real cavity, we have to carve out more memory for collisions, which means we have to drop the problem size here, the mesh size down, because we have a lot more work and a lot more memory with the particles. Our largest run on R3 at a pressure of 1 torr, we had 500 billion particles running in this mesh. This is just a convergence study for those meshes. You can see here, this is what we care about. We care about the currents, right? We want a peak current to see how high the current's going to go, how fast it increases, to understand how it's going to damage our components. And you can see here that we are getting mesh convergence. So it's just a pulse going out to 2.5 nanoseconds. And you can see that we can identify the peak, and we're getting mesh convergence there. We actually could not run the R3 mesh on any of our capacity machines. We didn't have enough nodes to fit this problem. So what we really care about to get these currents is we need to perform a pressure sweep. In this case, it was 18 points. But we operate under different pressures, and the maximum current in the plasma is going to depend on what pressure you're at. So what we found is that we had to run on the R3 mesh, so we're talking 512 nodes, 2,000 GPUs per run. It takes us about a little over 2 days to run out to 5 nanoseconds, which is what you need to really identify the peak current. Although the analysts want to run out 50 to 100 nanoseconds, so you can see this is goes into the weeks time scale here. So this is the first result. This is ramping the pressure from 0 up to 0.7 torr, where we found a maximum peak current. And so the green dotted line there, that's the X-ray pulse coming into the reactor. And you can see about 3/4 of a nanosecond later, the current spike from the plasma hits the device. So the solid lines, that's just a moving average. You can see the kind of random motion. Those are the actual point values as we move in time. So you can see that at 0.7 we have a maximum. If we keep increasing the pressure now, I had to split it up because we have so many plots here, but it starts at 0.7, the black line, then moves at 1 torr to the red, and you can just see that the peak current is now dropping. And so we ran this out all the way up to 8 torr. At 8 torr, the system actually went unstable. You can see our solution went unstable. So we believe we need to go actually to the R4 mesh if we're going to go to higher pressures. Although at this point, we always want to push it as far as we can go for knowledge reasons, but we did find our peak at 0.7 where our code does work. So we successfully identified this. We have a lot of questions now based on the data, and our next campaign on the machine, we're going to be pushing the larger meshes. From a scaling standpoint, these are the 3 meshes. The solid, or the dashed line, the black dashed line, that's the weak scaling study. That's keeping work per node constant. So you would like to see that flat. It's not, but it's not exploding too badly. And then the solid colored lines for one mesh, that's just your strong scaling study. So you can see we're not perfectly scaling. If you can see, I don't know if anyone can see that gray line there. That's that's ideal strong scaling. We're not quite there, but we do get good scaling, so we're pretty happy with this. To actually generate this study, it took a lot of time just to kind of balance the memory use to get these problems to run. So there was quite a bit of work there because the older machines have half the memory and take quite a bit longer to run. So trying to balance the study to get meaningful results took a bit of time. I mentioned there's the big 3, particle push, linear solve, and particle collisions. So these are the sub-timers for that system. You can see that collisions pretty much dominate on all 3 of the meshes. Our particle update was very close behind that. But what's really changed here now is the linear solve. You can see that the linear solve is pretty much flat. It's pretty much latency bound at this point, right? I mentioned compared to the original results on the simple scaling cavity, we've got 1/4 of the work. So there's just nothing here. We're just doing MPI communication across the board. So it's a little bit different for these real problems. Collisions were a little bit surprising to us in the sense that that was all just very local work within a cell. But you can see that's not strong scaling well. We expected that to do better, so we have to look at that. I know there's a sort in there and some other things that might be causing us issues. So you might ask, well, we're not near the strong, or we're in the strong scaling limit. If we went to lower node counts, do we see better scaling? And so we tried to back it up, but we didn't have enough memory. We couldn't do it on the R3 mesh, the blue line there. So these are the smallest problems we could run. We could back up a couple of points and barely fit it on the node. So we believe, we've tried R4 at 4,000 nodes. We believe it's run out of memory. So we have to actually push that to 6,000 to 8,000 nodes to get the next mesh to run. If you're curious of what the memory use looks like, it's really dominated by particle work. So this is the memory use per MPI process. So depending on how you, even though it's a unified memory machine, depending on how you allocate the memory usage, it gets reported differently. So you have to use the get R usage or hip mem get info to get the two pieces and combine that together. So I'm just showing that here. This is per MPI process. So you can see on the R2 mesh, there, each of these MI300As has 128 gigabytes. We're using 80 gig just on the device and then another 30 on the host. But this blue line here, the maximum, that tracks with the number of particles in the system, basically. So the particles flood in, and we're allocating memory until we get up to that big. So the memory requirements are right on the edge with this machine. Since there's a lot of linear solver people in the crowd, here you go. This is your slide. The blue, the red, and the black. All right, this is the number of linear solve iterations. For each of the solves, there's one solve per time step. And what you can see, there's one mesh that's run at 512 nodes for R3, and then it's just different pressures. The blue, the red, and the black are just different pressures. For the most part, it's bounded at about 100 iterations, but you do see this scatter all the way up to 175. So people not happy with 200 iteration. I'm extremely happy with that. I know there was talk earlier and they said they didn't want 200 iterations, they wanted 20. But we're happy with this. But that scatter, that's particles create noise, right? They're random, so there's a lot of noise in the source terms for the electromagnetic systems here. So, but the iteration counts are pretty constant, so we're happy with this. Even though the linear solver's latency bound, we'd like to see it faster, but we know it's all in communication at this point. So we also had a comparison where we could fit data on CTS2. So these are the Sapphire Rapids nodes. So it's a dual socket Sapphire Rapids. The red is the Sapphire Rapids CPU. The blue is the GPU. This is kind of the more disturbing part that we really want to work on next. You can see that at the low end, the low node counts, yeah, we're a factor of 4 faster, but if we go into this strong scaling regime, the CPU continues to strong scale where we tail off. We do have a lot of issues that we know that to fix this, and we're kind of working on those now. So one is that we've only refactored kernel collisions, partly to work better on GPUs. We have to finish that work. We believe a lot of this too is kernel launch overhead. Now, there was a KKP report that we had to do as part of a milestone 3 years ago, and one of the things it mentioned was how many kernels do you launch over your run? We're launching about 4,000 GPU kernels per second. So at least on some of our problems. So we are launching a lot more. And if we compared that to the other codes that we're running, one of our aerodynamics codes, we were like 4 times as much. So we want to do some kernel collapse. We also had to remove UVM, and there were a lot of fences that were needed for UVM. Not all of those were removed. So actually we have a ton of fences that we believe we can pull from the code to speed this up. So we think we can drop this blue line quite a bit lower. And we also want to incorporate the graph, Kokkos graph capabilities, because that lowers the overhead of kernel launch as well when you're reusing the same graph. We also need to look at, we do some complex things. We have virtual functions on device and we use atomics. And those don't always work well on device kernels. So we want to evaluate the effect these are having on the kernels. There's also quite a bit of warp divergence in our kernels as well. You can imagine with particles, do they collide or not? Do they hit a boundary and leave the domain. There's just a lot of things happening with the particles. And we'd also like to overlap the computations a little bit better. We have some ideas on that where while we're doing the linear solve, since it's latency bound, if we move that to like a smaller node count, we can use the other nodes to start the collisions early. So there's things like that we can play with too here. Last slide. One thing that surprised us, this caught us on the MI300. So we ran on the MI250s, and we didn't see any problems. But what we did see was that on the MI300s, because it had unified memory, they enforced cache coherence across the GPU and CPU. So it turned out the atomics were a lot slower, and we were using a lot of atomics. So you can see the blue dotted line. When we first jumped on the MI300s, we were much slower than the CPU kernels. But once we refactored our algorithms to use less atomics and have less contention in them, you can see that we got much better performance, the solid blue line there. So it was just a little bit surprising, but this was kind of a one-off thing we hadn't seen before, even on other GPU systems. All right, so with that, I'll conclude. El Capitan has allowed us to run the largest most accurate simulations to date of these cavity problems. Before this, there was no demonstration. We could do it, do a parameter scan at the accuracy we needed in a reasonable amount of time. So this is really exciting to our analysts that we're going to be able to get this faster turnaround. We see decent scaling of the algorithms. Obviously, we're not done. We've still got a lot of work. But this is not something we can currently do on our CTS systems. So. That, I'm done. I'll take questions. Yep.
David, so when you were doing this memory footprint checking, you said you were using get our usage and hit mem, get info. Do you have a sense of how accurate that is versus, say, like what proc mem info or whatever any of the system stuff would report? Or?
I did not experiment. So what I did, the smart thing is to contact HPE and AMD. And HPE said, we're writing a tool. Here's how we're writing our tool to do this assessment. And they told me use those two calls.
Okay, now they gave you conflicting information to me. They told me to ignore anything in the code and check the proc stuff. Okay.
So Roger, I'm testing it now because if we use huge pages, I'm not quite sure if get our usage is reporting.
Yeah, that's exactly why they told us not to use these things. Yeah,
so I know if you look at NUMA maps and the proc PID, NUMA maps, it'll tell you, or NUMA stat would have reported that as well. I'll find out.
Yeah, I'd love to hear it. Yeah.
Well, the other thing about that is the HIP reporting is telling you what has been allocated through HIP.
Yes.
Not what's been allocated through HSA, like in the NPETch implementation, which is at a lower level and maybe allocating other memory too.
Okay.
So there's other subtleties that might be missed.
Okay.
That I saw on Frontier. I don't know for sure whether it's true on LCAP yet because I haven't really studied it. So.
Yeah. I'll ask. I'll follow up with the HPE people. Yeah.
The other one's a completely unrelated question, but what collision model do you use for these particles? Just from a hat I used to wear.
So DSMC, the direct simulation Monte Carlo, it's just a elastic two body. That's the most I know about it because I don't handle the collisions. So we limit it, the cells, we limited in our merge to 1,200 particles per finite element cell. So you would have some fraction of those colliding. I don't know if that's enough to answer your question.
Does it also have a hybrid peak model in it, with like kinetic ions, fluid electrons, something like that?
There is hybrid work, but it's more on the research side. So we have shown results in the past, but that's kind of been lower priority work for us. But there is a hybrid capability, but there's a lot of research that has to go on to actually make that useful.
Already, last question.
Roger, do you have a feel of how many degree of freedom you can feed your GPUs for this type of focus?
How many degrees of freedom? So let's see. I don't have a number for the matrices. In terms of finite elements, right, we're using linear elements, but it's Nedlick and Ravier-Thomas elements for E and B. Well, actually, so we only solve the E. So, you know, it's just one on each edge. So we were running, you know, 600,000 finite element cells at the high end of that strong scaling study. So that kind of gives you how much we're fitting on there. But we don't try to maximize the mesh, like the PDE mesh. That's part of our problem. Is it's two problems in one. There's a PDE solve, but there's also particles in the PIC mesh, and we reserve most of the memory for the particles. So we actually have a very coarse mesh. If you were thinking of typical PDE codes, pure PDE codes, these meshes are much coarser than normal. So we don't, yeah. I guess I don't have a good good answer there, but that's why it's latency bound. It's in a regime we normally don't run Trilinos.
Alrighty,
That's-
thank Roger again.